In this section, I'm going to focus on the direction of vectors. So I'm going to stick with 2D vectors for now, just because I think it's easier to approach some of these concepts. So I have here an equality where, say, the Cartesian coordinates of a vector are equal to its direction times the magnitude or length. So magnitude is the length of the vector. The direction is where it's pointing, and it can be represented by two ways. One is the unit vector, basically a vector with length 1 that has the same direction as the vector I'm dealing with. So in this case, I have OP, which is, let's say, my main vector, the vector I'm dealing with, and I have OU, which is a normalized version of it. So how can I calculate the length of a vector? I can apply the Pythagorean theorem, and as you can see here, and if I put in, if I rearrange the expression in isolate length, I get this. Of course, if I'm dealing with 3D vectors, I have to put Z in there. But for now, let's say that I have this equal to 6 and this equal to 8. So I will get something like the square root of 36 plus 64, which is 100, so it's the square root of 100, which is equal to 10. So this here is equal, let's say it's equal to 10. So this is a way to calculate the length of a vector. Of course, it's not very interesting to do this explicitly with nodes, and thankfully I have these nodes that do that for me. So I have this length by AS tool for 2D and the native length node for 3D vectors. Now, to calculate the unit vector of any vector, I basically have to divide its coordinates by the vector's length. So in here you can see that, and so basically if I apply that here, I would say that the unit vector here would be 0.6 and 0.8 on the y-axis. Basically I divide 6 and 8 by 10. Now I don't also need to do this by myself explicitly. I have this normal node by AS tool, and I have the normalized node, the native one. I also have this one by AS tool where I can normalize 3 vectors in one go. So these are the two main groups to deal with the length of a vector and its normal or its unit version. And we can see that a position vector can be decomposed into a unit vector that basically contains the direction of the vector and its length, and they can be composed back. Now, these operations won't make much sense for vectors that sit on the origin. They have no direction, they have no length, so all of this makes no sense, and sometimes it's good to check for these cases so you can weed them out and avoid having issues in your calculation. Now let's look into the conversion between a unit vector and a rotation angle. So a direction can also be represented by a rotation angle. Basically, what's the angle that I need to rotate the reference unit vector so that it becomes equal to the unit vector of the vector that I'm dealing with. And so that's another way to deal with direction. And so sometimes it's useful to manipulate the unit vector. Other times it's useful to manipulate rotation angles. And so let's look into how to go between the two. So here I have the unit circle where the unit vectors lie on, and I have here this vector OP and have its unit vector OU. And here I have the trigonometric functions which create a relationship and right angle triangles between the angles and the sides of the triangle. So this is a bit of a key between the coordinates and angles. So you have that the cosine of the angle is equal to the adjacent side over the hypotenuse. Now, if I'm dealing with unit vectors, they have length 1, and so if I transpose this to here, I can see that the hypotenuse is equal to 1. So this makes these calculations easier. So I can say that the hypotenuse is 1, so the cosine of the angle here is just basically equal to the adjacent. On the same light, the sine of the angle is equal to the opposite over the hypotenuse. So if the hypotenuse is 1, I also get this much simpler. So the sine of the angle is just equal to the opposite side. So if I put this back here, I can, if I, let's say that I have the angle of this unit vector, but I don't have its coordinates, then I just need to apply the cosine and the sine function to the angle, and I will get the coordinates. So this is one way to go from angles to unit vector coordinates. You just basically apply the cosine and the sine for x and y. This Wikipedia animation shows clearly the cycles of cosine and sine functions and how they map the position of a point point on the circle. Now, in this process, there are things that are lost. So for example, here I have a note where I say that angles with the same direction will have the same unit vector. And it seems that there's nothing wrong with that. The thing is that with rotations, you can have rotations that have different turns. So for example, here I have minus 660, 300, 60 degrees, 420, 780, etc. They all have the same direction. But the thing is, they have different turns. So there's different, there's different rotation data involved here, but they will all have the same unit vector. So just because they have the same direction, basically there's nothing here that makes a distinction between the turns that they had. So there's something that is lost in this process. So here I have an example where I have 60 degrees, 420, 780, and they all have the same unit vector. So this is something to keep in mind when using coordinates when going between coordinates and angles, is that this notion of turns is lost. Okay, so let's look into how convert 2D unit vector coordinates back into angles. Now, the way to go about it is to basically use the inverse functions. So in this case, the arc cosine and the arc sine. So apply the arc cosine onto the x coordinate and apply the arc sine into the y coordinate. Now, they will not give me back 360 degrees range right away. The arc cosine will give me something between 0 and 180 for both sides, and the arc sine will give me something between minus 90 and 90 degrees. If I combine the two, I can build up with logic nodes, etc. I can build up something that gives me the standard angle between 0 and 360 degrees. There are nodes, though, that make this much easier for me without having to go into a complicated setup every time I want to do that. So the first one is the arc 10 node, which basically gives me a range between minus 180 and 180. And then there's the angle node. Both of them are by AS2. And so this one has more options, as we can see here. Let me go into Lightwave. And so I've hidden the wheel path and the wheel, and I've put up the angle control and the angle color object. In the angle color object displacement node editor, I have here this setup, and we have here this angle node, and you can see that there are some options here. Invert will basically just change the sign of or the orientation of the rotation or the angle, and round will basically be a switch between two ranges. So if I have round off, I will have a range between minus 180 and 180. If I have round on, I will basically have a standard angle that goes from 0 to 360. So these are the two options that go with round off and round on. These other two are just if I have the invert option on or off. So this is for round, this is for invert. So basically with this one node, I can have 4 types of ranges in a way. So there are many types of angles that can be taken from one unit vector, but I'm going to first check onto the decomposition of this. So I have a position vector, and so here I made a decomposition from position to unit vector to length back into position. Now with these operations, I can make a decomposition from position into angle and length, and then from the angle I can go into unit vector and back into position. This allows me that in between these, in this space here, I can manipulate the angle and I can basically compose my vector back. So let's see an example of that. So I have here this object, and I have here the same decomposition that I had here. So basically I have my position vector decomposed into angle and length, and then the angle goes into the cosine and the sine function, and I multiply that. So this gives me the unit vector, and I multiply that by the length that the vector had. So in this case, I'm just doing that for x and y, and I'm going to leave z as it was. So what this allows me to do is, let's say that I offset the value of the angle. Well, this means means that I can basically create a rotation routine. So if I come here and I put add, and I put in here this and this, and if I put a value in here, basically I'm rotating the positions. That's basically what I'm doing here. Let's say that I want to drive this with something else. I have this object here, this null, and I have here an item info with it, the angle control. And so I have its position X and Y going into another angle node. So I'm going to use the angle that the position of this null makes with the the reference unit vector to drive the angle that it rotates the mesh. So with this, basically what I've done is I created a target routine. So now the x-axis, or in this case, this arrow here is targeting my object. So it's a basic target routine. Right, so back to this topic here. There are many ways to, there are some ways to basically get an angle from a unit vector. You can see here, for example, with arc cosine, I get something from 0 to 180. With arc sine, I get -90 to 90. With arc tangents, bit a mess. With these, I get full rotations, etc. So there are many ways to go about it. Of course, this is all possible because I'm working with a plane that is very, it's well defined. So I have something where I have the reference, the axis of X and Y defined for me. If I have a plane and let's say, something like this, and I don't have no axis defined in it, it's quite hard to do this. But since I'm working on contexts where these are defined, these are very easy. So let's look into that. I have this object here, and I'm going to turn on VPR. And what I have here is, something explaining what's the color code going on. So green is 90 degrees, yellow is 180, and white is 360. Black is 0 degrees, purple is -90, and blue is -180. So you can see here that the mesh here makes 0 degrees with the x-axis. And so let's look into the several things that are going on here. So I made this compound called angles 2D, and basically allows me to have all of these types of angles that I have here. So this unit vector, if I'm looking at it from a standard angle perspective, it has 230 degrees. But if I look at it as if I want to get the shortest angle with this line, well, I can say it has 50 degrees. Or if I assume that vectors that point in this direction are negative and vectors that point the same direction that the y-axis points are positive, I can say that this vector has -50 degrees with this line. So it depends if I have access to this direction or not. Now, in another way, I can, instead of worry just about the line, maybe I worry about the direction. Let's say that I really want the angle this vector does with this direction. So in this case, it's the value. It's different. It's this value here of 130. So this does 130 with the x-axis. Now, if I again take into account the y-axis to define that this is positive and this is negative, since this vector is pointing down here, I can say it's -130. So these are some examples, and I have them here in this compound as an example as well. It's a demo of types of angles you can get in a 2D plane. So here I have 0 to 90. -90 to 90, so now I can see some purple here, as you can see. 0 to 180 goes from black to yellow, and this is what, for example, the arc cosine does. And then I have -180 to 0 to 180, and then I have 0 to 360. So from here to here goes 0 to 360. And opening up the compound, you can see that basically I use another version of angle node. So here it's just basically the ones that we saw before were just one single angle. And I have these options here. This one uses two angles and compares them based on not a value of angle, but a value of coordinates of the unit vector. So it normalizes the positions that I've put in there and compares them. So it has the same options, even though they are a bit hidden, but are the same invert and round options in there. And after that, basically what I've done is I used the sine and the cosine functions so that I could have them back into a coordinate format. And then I used the arc sine and arc cosine to basically do all of these options. I could, of course, have the 0 to 360 and minus 180 to 180 done by this node alone. The idea was here to demonstrate how I could use the arc cosine and the arc sine function to do these. So let's see one thing. This node uses two unit vectors and compares them, but here I'm just using one. I'm just using the world spot of this object. So let's say that I want to change the reference vector. So here the reference for the angles is the x-axis. Let's say that I want to have this object here that I have the mesh rotate about and following and targeting to be the new reference unit vector, so that whatever is in this direction is 0 and the other angles are judged by that. So here I have an item info with a split vector on the position, and if I plug this in here, you'll see that the B input has an exponent of -1. So usually when I use that is to indicate that this is the context or this is the reference value. And so now you can see that wherever the object is pointing to is the reference value. So here is 0 and then it goes to 360. Or if I, let's say, put 0 to 180, this is 0 and this is 180. So these are some examples of cosine and of the trigonometric functions and their inverse counterpart. So one last thing is that, like I said, this works when you have defined defined coordinate axis. When you have, let's say, a sphere and you define a plane on its surface using one of these one of its perpendicular normals, and so even though you have the plane defined, you don't have the other two coordinate axes defined, x and y. So it's quite trickier to do these sort of evaluations and have angles that go from 0 to 360 or minus 180 to 180, etc. Now, the last note in the section I would like to give is, so we saw the conversion between angle and unit vector to angle. Now this was for 2D vectors. In 3D vectors, I'm going to talk more about this later, but in 3D vectors that's basically done with matrices, where I have a matrix converted into rotation angles, the same angles you are used to deal with here, the heading, pitch, and bank. So here I'll have two unit vector directions converted into angles, and then those angles converted back into directions. So this is a way to go back and forth between the two, and I'll go into the details about it later on when I talk about matrices. But keep in mind that just like in the 2D example, when I convert between angles and direction vectors, I lose the notion of turns.